So question 4. The first thing to note in question 4 is that they've given you these units not in base units. So we should convert them to 0.016 meters and 0.016 kilograms. Write that on the paper because it makes it less likely you'll make a mistake later. Part 1. We need to calculate the density of the steel ball used. So we need the formula for density, and that's here on your formula sheet. Rho is equal to m over v. Rho is the density. So rho is equal to m over v. So first of all we need to work out what the volume is. I'm going to write that up here. The volume of the steel ball is the volume of a sphere. That again is on your formula sheet. The volume of a sphere, 4/3 pi r cubed. So it's 4 divided by 3 times by pi times by r cubed. Now let's just be careful. It says diameter there, so the radius is going to equal 0.008 meters. So just be careful that you don't put the diameter in here instead. So that's 4 divided by 3 times by pi times by 0.008 all cubed, like so. Put that in the calculator. Turn it on. 4 divided by 3 times by pi times by brackets 0.008 close brackets to the power 3, and that gives us 2.14466 ... and the units there are meters cubed, and the reason they're meters cubed is because we changed this into meters to start with. Much easier to do that and work this out in millimeters cubed and then have to convert it. So to progress on this one, calculate the density of the steel ball used. We get the mass, which is 0.016. We divide by the answer that we just got. Oh, I've made a mistake. That's times 10 to the minus 6. That's a big difference. 2.14466, etc. times 10 to the minus 6. And we do equals. So 0.016 divided by the answer we just gave is 7,460, which sounds about right. So that's 7500 to 2SF. 7500 there to 2SF. In the test, the ball bounced back to a height of 0.85 meters. Calculate the speed of the ball just before the impact. Now this is a bit cheeky because this piece of information actually corresponds to this question here. So you've got to realise that it's irrelevant for this part here. Now there are two ways that you can do this. One is using SUVAT and the other one's using energy. I'm going to show you both ways. I'm going to do SUVAT for this question here and energy for this question here. Right, so we can use SUVAT because there's a constant acceleration. So let's mark that onto our diagram. We know what the acceleration is. The acceleration is equal to 9.81 meters per second squared. Draw it on the diagram. It's always useful to draw things onto the diagram. Right, we need an equation. So you look through your SUVAT equations, and the one that's most useful is v squared is equal to u squared plus 2as. V squared is the impact of as the ball drops down here, it's under acceleration of this. It's going to speed up. That's going to be its final velocity just before it hits here. That's its initial velocity, which is 0. A is there, and the displacement is that amount there. So v squared is equal to nothing plus 2 times by 9.81, the acceleration, times by the distance, 1.27. So here goes. 2 times by 9.81 times by 1.27 gives us this, but v is the square root of that, so v is equal to square root of the answer, 4.99 meters per second. So that is 5.0 meters per second to two significant figures. Right, so that's a way of looking at it using SUVAT. Up here, we're going to do the same thing, but we're going to use energy now. So now the ball is rebounding, and it only comes up to a height of 0.85 meters. So, calculate the speed of the ball just after the impact. So once it's impacted, it's lost a bunch of its energy. Once it's impacted, it's got some kinetic energy and it's flying upwards. And then it's going to lose that kinetic energy, and that's going to transform into gravitational potential energy. Once it gets to the highest point on its rebound, then all of its initial kinetic energy after the bounce will be transformed into gravitational potential energy. So we can equate the two. So the kinetic energy at the start will equal the gravitational potential energy at the end. And that's because all of the energy will be transformed, because it will have no kinetic energy when it's at the top, it will be stationary. So a half mv squared is equal to mass times by gravity times by delta H. So those are your two energy equations. Those two cancel. If we move that 2 over there, we get v squared is equal to 2 times by the acceleration due to gravity times by the change in height. Now you'll notice that that is exactly the same as that. So suvat and energy will give you the exact same thing at the end of it. So that's equal to 2 times by 9.81 times by 0.85. So here goes 2 times by 9.81 times by 0.85 gives you 16 and a bit. We need to square root that to get what V is. So V is equal to 4.0837 ... meters per second, which is 4.1 to 2 significant figures. Right. Calculate the change in momentum of the ball due to the impact. Okay, so the change in momentum is momentum, P, is equal to mass times by velocity. Now initially the ball is going down at 4.99 meters per second, and then it's going up at 4.0837 meters per second. So the change in momentum is going to be quite big, because it was going that way and now it's going that way. So to find the change in anything, you have the final value and you take away the start value. So the final, take away the start. Now momentum is a vector, so it's very important to remember the direction of the ball in each case. So we need to assign one of these directions a positive value. So what I will do is I will choose down as positive. So down is positive. It doesn't matter which one you pick. Okay, so the final velocity, final momentum is going to be the mass of the ball, which is 0.016 kilograms, times by the final velocity, which is going to be 4.0837. But that's going up, and this, I said down was positive, so that's going to be a minus there. And then we're going to take away the start value, or the start value is going to be 0.016 times by 4.99. So if we do that calculation, 0.016 times by minus 4.0837. Right, we do that calculation. How do I do a minus? Okay, so we do that calculation, 0.016 times by minus 4.0837, take away 0.016 times by 4.99, and that gives us a momentum change of minus 0.14517 ... So to two significant figures, that is minus, I'll put that in brackets, 0.15 to two significant figures. Now the minus sign is simply saying, well, the down was positive, so which direction is the momentum change? Well, the momentum change is upwards, because it's negative. So it was going down and now it's going up. So the momentum change has been in the upwards direction. That's why the minus sign's there. You would not be penalised if you didn't have that minus sign in or if you hadn't worried about it. The contact time was 40 milliseconds. So let's quickly change that into base units, 0.040 seconds. Write that on your paper. Calculate the average force of the ball on the lens during the impact. So for this one, we need Newton's second law of motion, which is written on your formula sheet, I am sure. So here it is, force is equal to the change in momentum divided by the time taken for that change. It's Newton's second law. So force is equal to the change in momentum divided by the time for the change. So the change in momentum is what we just had, so 0.14517 divided by the time for the change, 0.040. So we want our answer to the previous question, 0.04, gives us minus, again, 3.62948, so that's minus two significant figures is 3.6. So again, the minus sign, you would not be penalised for not having worried about it throughout this. 2SF. Explain with reference to momentum why the test should also specify the material the plinth of the lens sits on. This is explained, so we need to refer to some physics in our answer. Well, really, if you want a controlled test, for the results to be the same every time, you've got to make sure that the plinth that the lens rests on is the same. Because if we changed it to something that was softer, then you can imagine that as this came down, it would absorb some of the energy, increase the length of time for the collision, and thus reduce the force. So any change in the lens plinth would change the force that we're actually dropping the ball, or the force of the ball on the lens. So let's write that down then. Pick one or the other. A softer plinth, you could pick a harder plinth and do the same reverse argument, would increase the length of time of the collision and therefore reduce the average force. Therefore, the plinth must be controlled. So we've got to control the material of the plinth in order to get standardized results for this particular experiment. You could have said a harder plinth would decrease the length of time for the collision and therefore increase the average force.